Hello everyone and welcome to another video of Vivek Learns. In the last video of PepCoding Level 1 that we had made, we were revising the concept of stacks. So we had started the revision of stacks module with this balance bracket question, and then we had went on to the new questions. So in this balance bracket questions, we were pushing whenever we were seeing whenever we had an open bracket or any other element, we were pushing and we were popping till and whenever we encountered a closing bracket, we were popping all the elements till we encounter a opening bracket. Then we were popping the opening bracket, and before popping we were checking if we already had an opening bracket. So if we already had an opening bracket, then there is no element between these two opening brackets, and hence these were duplicates, right? And then we discussed this question where we had balance. We had to find which were uh, the balance brackets, like which, so suppose we have a opening bracket for this, but we didn't have a closing bracket. So we had to find such use cases where we returned true or false based on the inputs. If it is valid, then we return true, and if it is invalid, we used to return false. So here also, if we encounter an open bracket, we used to push, and if we encountered a closing bracket, we used to pop, right? And before popping, we used to check if the corresponding closing bracket had the corresponding opening bracket. If not, then we used to set the is valid flag as false, and we used to return. The next question that we solved was the next greater element to the right. So what we did here is that we started from the rightmost element. So the next greater element of the rightmost element will be -1. So we used to put -1 here. So we had seen two methods that we can solve. So here we are just putting the index, or we can put directly -1 here as well. And then we used to check. So we also had a stack where we used to push the last element that we had, and if we then we started iterating from the length my array dot length -1 or -2 element, right? So we used to start the iteration from there, and we used to continue the iteration all the way to 0. And if we encountered a number which was greater, then we used to pop. Okay, and if we hit the bottom of the stack, we used to have -1 inserted into the result array, or if we encountered a number which is greater, then that number is the next greater element, and we used to have that number, which was the stack dot peak, inserted. So this is how we had solved this question, and for the next stock span question, we had to find the the number of days which had passed between the previous I and today, right? So here also this was similar to the next greater element to the left question. So to find that, we pushed 0, we pushed the index right here, and in the array we inserted -1. We started the iteration from 1 all the way to result array dot length, and we used to check if the element that we are iterating, is it greater than whatever is present in stack. If it is greater, then we used to pop till we encountered a greater element, or the stack was empty. If the stack was empty, we used to insert -1, or if we found a greater element, then we used to insert that into the array. And once we got all the greater elements to the left, right, what we used to do was that for the entry -1, we used to say that um, there is no element greater to the left of these numbers. So what we used to do, we used to have index +1 for such variables. And for the other variables, what we used to do, we used to have the index minus the index that we had stored already, or we could also do I minus stack dot peak here directly. So this was all about the revision that we had done earlier. So let's revise the next question that we had solved, which was this largest area in histogram. So we were given an array here and we had to find the largest and these arrays, these elements of these arrays, they represented bars, right? Bars in a bar charts. And we had to find the largest area in that histogram. Okay, so let me have this here. So what we did here was that okay, let me solve it here once. So let me have a line and have this bar chart created. So we had this bar chart. Let's have it here. And in this bar chart, we used to have 6 and then 2, say 2 and then 5. Say 5 from here, then 4, say 4 from here, then again 5, then 1, then 6 again. Okay, so we were given this, and the width of these bar charts is 1, and we were just given the height, and we had to find we had to find the largest area of the histogram which is formed. So if we consider only this bar chart, the area formed by this bar alone is 6 times 1, which is 6. Area which is formed by this is 2 times 1, 2. Similarly for this will be 5, 4, 5, then again 1, and then um, we'll have the area which is covered by this as 6. But we had one more condition, like we could club the areas that are formed. So what we could do was we could extend this, something like this, and we could form such areas. So the largest area, which was the answer of this question, was 4 times 3, okay, which was 12. So what we did was we first tried to, have these columns expanded, these brackets expanded, and what we found was that these could expand till the next greater element to the left and not the next greater element, the next smaller element, right? These could expand till the next smaller element to the left and the next smaller element to the right. Okay, and uh, so we had to find those elements first for the left boundary and the right boundary. So if we consider this array that we had, so ARR, let's say, and let me have the number here as well. So these are the indexes that we have. Okay, and then we have the left boundary, which was, so the left boundary meaning the next smaller element to the left. So it will be -1 for this. Then we'll have, let's have two spaces. Okay, so for this it will be -1 only. Yeah, for this it will be 2. For 4 it will be again 2, right? And for 5, for 5 it will be, so what we can do is that we can store the indexes of the elements which are having the left boundary, right? So for 5 it is 1. The left boundary is 1. For 3 it is for the third element, which is 4, the next smaller element to the left is present at position 1. For 5, the next small element to the left is present at the position 3. For 1, there is no mm, smaller element, right? So we insert -1 for 1. For 6, it is present at 5 itself. Similarly, we can have right boundary also here. Yeah, so if we have a right boundary here, then we do -1. So what we can do here is that we can consider a valley, right? That's what we had assumed when we were solving this. So if we fall into this valley, we fall into ARR dot length, and if we fall into this valley, we fall into -1. So we can consider the ARR dot length, which is 7 here, and for 1, the next smaller element is also 7. Okay. For 5, next smaller element is present at the index 5. For 4, it is present at 5 again. For 5, next smaller element is present at 3. Okay. For for 2, the next smaller element is present at 5, the position 5. For 6, it is present at 1. Yeah. So once we find this left boundary and right boundary, what we can do is we can subtract their indexes. So how do we get the area? So area will be length times the width, right? So how do we get the width? So to find the length, we'll get it, right? Whatever the length is of the bar chart, we'll get that length. And how do we get the width? The width is nothing but the right boundary minus the left boundary minus 1. So if we see here, mm, where is my pen? This is, let me have it here, 0, 1, 2, 3, 4, 5 here, and then 6. So these are the basically these are the indexes that we have, right? So how do we get um, the area, right? So we can do 5 minus 4, 5 minus 1, which is 4 minus 1. So we have to find the index of the next greater element to the right minus the index of next greater element to the left index, and then we have to subtract that, and we had to subtract -1 from that to get the width. So meaning 5 minus 1, 4 minus 1, 3. So that is how we got the width, and the height is 4, right? So yeah, that is how we had solved this question. So that will be for 4 if you see your 5 minus 1 minus 1. So we'll do kind of right boundary, right? Right boundary minus left boundary minus 1. So this is how we had got the answer. And then we had the logic for the max area. Okay. So let's try to solve this question again of the largest area of the histogram. Let me comment all this part and let's try to solve it again. Solve it again from here, let's say. I cannot see the solution. So we find the left boundary and the right boundary first, right? Let's say right. Or we could just have length. Similarly, we have left boundary as well. Let's say LF boundary, LFT. So we need logic here to have the next greater element to the next smaller element to the right, right? Right, correct. So we iterate over the array, which is this array. And what do? We iterate till array is not empty, and we need to have stacks for those as well, right? So let's create a stack of integers. Let's say right stack. Okay, so what do? We insert for the right stack, the rightmost element will be stock that right stack dot push, right? We have push, yes, right stack dot push arr dot length. That is the first thing that we do, and right boundary of arr dot length of right boundary of the last element minus 1 is equals to arr dot length. So we push arr dot length minus 1, right? What do we push into the stack? Yeah, the last element, and we push arr dot length here. Yes. So once we do this, we start the iteration, and what do we compare in the iteration? We first check if right stack is empty or not. Right stack should not be empty. And we have another condition where arr of I. So we start iteration from the second last element. Okay. So we'll iterate till I is greater than equal to 0. And arr dot length minus 2. Start the iteration from the second last of arr dot length minus 2, and we'll continue till I is greater than equals to 0, and we compare if we find a smaller element, right? If we find a smaller element, then we pop smaller element dot then arr of stack dot peak, not arr. We'll require this, right? Right boundary of stack dot peak, right stack, right? Once we check if it is empty, and if we find a greater, if we find a smaller element, we do right stack dot pop, right stack dot pop, and if we encounter that the stack is empty, if right stack is empty, then what do? Then there is no element which is smaller than the uh, element to the right, which is smaller than the present element. Then we insert into the array, which is this right boundary array. What do we insert? We insert right boundary of I is equals to minus, we insert array dot length, right? Yeah, because we are considering the right side. Else, what do we have? If stack is not empty, Then we'll insert stack.peak, whatever is present in stack.peak, uh, right stack.peak, right? Right stack.peak. Yep. So, and we have to push the elements. So we have right stack dot push. What do we push? We push I, right? The index is what we push. Mm, so what we can do is that we can check this, but let's have both the things first and let's check then afterwards. So we'll have to create another stack here called the left stack. So this is the left stack, and we insert into the left boundary and then left boundary dot length. Then we have, so we'll start the iteration from 0 here, not from 0 but 1, and we push 0 here. Okay, so first let's try to have all the right stack, right boundaries replaced with these left boundaries. So we'll not have this here, right? We'll have ARR. Yeah, have ARR because we are considering that as the base. Yeah, and we are iterating over ARR only here, right? So we'll have ARR here as well. Correct. So let's replace all the occurrences of left stack is not empty, then we pop from the left stack, then we check if left stack is empty, then we insert -1 here. It is no element to the left is smaller than the element, right? Then we push into whatever is present in left stack or to the left stack, and then we push into left stack dot push left stack dot, in the left stack we push it, right? So let's check if we have any right reference here, and we insert to the 0th element. What do we insert? We insert -1, seeing that there is no element to the left which is smaller than the 0th element. So if we find, we have to have left stack here also, right? Yeah, so what we can do is that we can first print it. So we'll have arrays dot to handy method, right? Arrays dot, similarly we can print the left boundary also. Yep, let's try to run it once. What is the input? Was 7652,454. 625, right? Then we have 1 and 6, right? No, we aren't getting the correct output here. So for these it seems to be correct. Let's see. So this is for the right boundary. So let's compare for the right boundary. Yeah, for right boundary it is correct. 7755351. Yeah, so it is correct for the right boundary. For the left boundary we are getting something weird. So we'll have 1. Why do we have 1? We should have -1, right? What did I insert here? Let boundary of 0 is -1, and when we start the iteration from, oh, okay, we forgot to change the for loop conditions here. Let's try to run it now. And what were the elements? 6, 2, 5, 4, 5, 1, 6. Let's check. -1, -1, 1, 1, 3, -1, 5. Yep, that's the output. So once we get this, we can iterate over the array and we can find the areas. So let's have a max array, a max area variable declared as 0. So we'll store the max area, whatever it is in this variable, and we iterate over the array that we have. And what do we check? If so, we can calculate the area first, or we can directly have. Mm, okay, let's calculate the area. Area is equals to right right boundary of I minus left boundary of I minus 1 times the error of I. Once we get the area, if area is greater than max area, then what do we do? Then we have max area is equals to area. Yep, right boundary of I minus left boundary of I times the error of I. So let's try to print the max area as well. Yeah, we get the expected output. So this is how we had already solved this question. In this question we were just revising this problem that we had. So yeah, that's all for this video. In the next video we will revise this sliding window question that we had solved. Sliding window maximum, which was an interesting question, but to discuss that it will require some more efforts and 2-3 concepts would be required. So let's discuss that in the next video. So that's all for this video. Thank you guys.